Welcome, this is Mr. Dahlstrom. This will be the last problem I'm looking at this evening. This is number 61. The reason I'm looking at number 61 from the AP physics problems is that it is another application of the principal axis theorem, but is also using that in terms of torque. And when I first initially went through this problem, I was wondering why I was having to use the principal axis theorem here, but for reasons that I'll explain in just a moment, I'll explain here. So what this problem has is that we have a disk. We have a uniform disk that is on some inclined plane. We have the height, we have theta. It tells us the distance here for how long the ramp is, and or at least that is the distance. We are given a disk of r, and some things that we need to realize what's happening. So some need to knows is that we are rolling without slipping, that torque is equal to I alpha, or the moment of inertia, times the angular acceleration, and also that torque is equal to RF sine theta. So the first thing here, what we're trying to find is what is the acceleration of the center of mass of this disk. Now, if you're just trying, first of all, when we have this torque problem, we're going to have to find acceleration. You're saying, well, where in the world does acceleration even appear there? So we have to remember there that A equals R alpha, and so that means alpha equals A over R, and this A right here is the A that we are trying to find. So we need to try to figure out, excuse me, what are the other variables here? So we can set the two torques equal to each other, because there's just another way of writing that R F sine theta is equal to I, and then I'll plug in what we already know about that, I A over R. So what is the F in this port? So we have to think about what is causing some type of torque to be had here. In order for this, so when I was initially looking through this, it's like, oh, okay, I'm just going to take the center of mass of a disk, which is 1/2 mr squared, and I'm going to apply it to this. Had this been an energy problem where I'm plugging this into a rotational kinetic energy problem, that may have been the case. But what's happening here is it's not just rotating. This is similar to the one where we had the dotted lines here, and you had the other disk here, and it's rotating about some single point. We have to realize that in the reference frame of the rotating disk, it's always in contact with the platform, and in order for it not to slip, there has to be some torque that is given, at least by by the weight, by the force of gravity, and also by the friction that's along there. And that's actually, we're going to have to find this acceleration, and then later on they're going to ask us what minimum coefficient of friction is going to allow us to, let me see here, what is the minimum coefficient of friction required to maintain pure rolling? When they say pure rolling, not slipping. So this acceleration means that this is the acceleration that we need in order to not slip. There is some amount of torque that's being given at this point here. So we can at least think for the first moment of time that we have a disk that is rotating, but not rotating about the center of mass here, but instead rotating about some point P, and really infinitely and many times. We can look at it at some moment in time later where maybe the radius arrow is pointing a different way, but it's still in contact with point P. So it's not just a purely rotating object. We can't just use 1/2 mr squared. We need to figure out what is the moment of inertia about point P here where we're in contact. So once again, using the parallel axis theorem, I equals Cm plus md squared. Once again, d is how far we are basically moving ourselves from the center of the axis of rotation. We already know the center of mass of a disk, of a uniform disk, is 1/2 mr squared. Excuse me. And how far, we're not rotating about here, we're displacing ourselves that distance, or we're displacing off that distance, and that distance is known as r. So for this one, like the one we did over here, how far we are displacing ourselves here is that d is equal to r. So we have r squared. So similar to another one we've done, we can just kind of call that 2 over 2 to make the math a little bit easier. And I equals 3 over 2 mr squared. So that's what it is. That's what the disk is about point P. So we now have our I. In this answer, this problem doesn't give you any numbers, so just all variables. We have to figure out what is this force. So what force in this case is giving us? So giving us the ability to roll. This force here is the force of gravity. So force of gravity times sine of theta. So R mg sine of theta. Because if there was no torque due to gravity, there would be no reason for this thing to start rotating. So you could imagine that some point along here has some force that's perpendicular to the disk at every single point that is causing this thing to rotate as it goes down. And that equals I. We just calculated I, not for the disk, but for the point around P, which is 3. I'll just try to do it all with 3 over 2 mr squared. Just to kind of show like there. And that's being multiplied times A over R. Once again, doesn't matter if it's big R or little r, big R or little r, they mean the same here. So I'll just keep it like that. So we can cancel some things out here. Excuse me. Masses cancel out, which is always kind of neat. One of these R squareds cancels out with one of these R's. And now we're left with R and R on both sides, so that cancels out with that as well. So we have G sine theta equals 3a or 3 over 2a. And we're solving for a, so we just rearrange this. A equals 2g sine theta over 3. So that represents our acceleration. Once again, we got this because we realized this was a disk that was not just purely rotating, but it was rolling about a point P. There was some torque that was being brought on by the force of gravity here, but also once again realizing why did we do the parallel axis theorem? It's not rolling. It's not doing this. So basically, I'm trying to explain it here. It's not like there's some kind of, it's not rolling down about some point like that. It's not doing this as it's going around. If it was something where it was somehow rolling around the incline that way, then we could use 1/2 mr squared. But the fact that it is being displaced upwards amount of point, and that there is a force here that's causing a torque, and that really depends on what the angle is there as well. So that gives us our acceleration. Part B has you doing the exact same thing, but it has it doing it for a thin loop instead. So what would you do? You'd find the center of mass for a thin loop. Plus mr squared again, because if it's a loop, you're still only displacing r, and you do the same thing. And if you did that for a thin loop, the acceleration comes out to g sine theta over 2. Okay. So part C I wanted to go into. So part C has a mixture of our net force equation. So here we had some torque, here was some net force equation. I've already done a little bit of work here. So what they're asking us for is what is the minimum coefficient of friction for this acceleration to exist? Okay. So if we were looking at our free body diagram here, if we're assuming that that's positive y, that's positive x, we turn that sideways. Sideways, we would have the x component of the force of gravity right, minus force of friction left, so Fg of x minus force of friction, equals mass times acceleration in the x direction. Just some reminders here of when to use cosine and when to use sine. If we see that this angle right here, reminder, is the same angle there. So Fg of y is connected to this axis here, so that means Fg of y is going to be Fg, mg cosine theta, and the one that's opposite of that doesn't get sine. So if it's connected to it, it gets cosine. Also a reminder of mu equals force of friction divided by normal force. That's also going to come up. So plugging in Fg of x is mg sine theta because it's not connected to the angle. Minus force of friction equals max. And then that's basically at this point, that's kind of as far as we can go without needing some more information. Remember, if we have friction, we have to take into account the y direction. And if we look at the y direction here, we have normal force up minus Fg of y, and it equals 0 because we're saying the acceleration only happens in the x. So Fn equals Fg of y, or Fn equals mg cosine theta. Remembering down here that mu equals force of friction times normal force, that means force of friction equals mu times F of n, and that right there gets plugged in right there. So this normal force that we found over here gets substituted in, and the A of x that we found up here, this basically is A of x, that goes right there. And it's all about simplifying. We're done with the y-axis. It's all about simplifying up to this point here. Mass cancels out. So we can do this here. G also, interesting enough, cancels out. G, G, and G. So we have sine theta. I'm actually going to call this 1 sine theta minus mu cosine theta equals 2/3 sine theta. The reason I called that 1 sine theta here is that if we put all the signs on one side, if I subtract this and add that over, 1 minus 2/3 is 1/3 sine theta. And when I move that over the other side, I get mu cosine theta. And if I solve for mu, dividing both sides by cosine theta, if you remember our trig identities here, that means that mu is equal to 1/3 tangent theta. And there we go. But all of that comes back from the understanding here that we can't just take the rotational inertia of the disk itself. We have to realize that it is rotating not about itself as it moves down here. It's rotating about a different point that is a distance r away from the original axis. And that's how we found this for thin loop is another part. That's part B. And then we plugged it into that part there, simplifying, and found that acceleration. Then when they asked us what's the minimum coefficient for the disk not to basically slip, it's all just setting it up using net force equations and simplify. It's really quite astounding that that's as simplified as it ends up being. That's why sometimes when you do things in variables, yes, it can get quite long and nasty, but you get these elegant solutions at the very end. So appreciate it. If you can go ahead and if you enjoy me, just say hi or something during your school tomorrow, or subscribe because I've done 4 tonight and I'm kind of tired. So have a good evening. I'll see you around.